and have a sophisticated build system where they have everything in pure C, but then they have files that on certain architectures will be used instead of the pure C that are written in assembler, which make the code faster. So let's see. So integer arithmetic. So what you find when you look in the sections is basically just a bunch of functions. This is a C function. There's where the output goes. This is where the input goes. MPZ underscore T is the sort of data type for all GMP integers. It's just some C type, etc. So these functions are for doing things like dividing and taking a remainder. We're going to use, in fact, one of these functions. But I didn't write this code by looking here to remember how to write it, since it's a little overwhelming. I literally looked at the Sage source code to see what Sage uses. Okay, so back to our story. What I do here is in Cython, I declare a couple of MPZ underscore T variables. I then initialize them. I do a little bit of arithmetic. Then I create a Sage integer. And it happens to have a Sage integer basically is just a pointer to an MPZ underscore T. So I take that MPZ underscore T and I set it to n raised to the power of D, where the arithmetic is done mod this power of 10. So that's what S will be equal to after I do this. This is kind of dirty because here I've taken a Sage integer, which is supposed to be an immutable object, and I've actually changed it in this line. So in Cython you can change anything, you can mutate things you shouldn't be able to mutate, etc. So you have to be very careful what you do. Finally, I converted to a string just using pure Python. Here I'm not going to worry about whether I use Python or Cython, or try to write it in some more low-level way, because my gut instinct from thinking about the mathematics is this is going to be where the most time is spent. But we don't know that yet. I mean, it could be any step here that's dominating the runtime, as far as we know. Okay, so let's try this out. So first, evaluate it. And the first thing to do after turning anything into compiled code is to see if it works. And I assure you, when I wrote this before, it didn't work the first time I tried this. So probably if you try to write something, convert it from some nice, easy-to-read Python into some low-level library code, the odds that it's going to work perfectly the first try is very low. So it didn't work the first try, but this is working. This is giving the same output as we had above, because I fixed any problems that I made up there. It didn't take long to fix them, but I had to fix them. Okay, so now let's time it, and this is sort of the moment of truth. How much of a speed up do we get over our 67 or 69 microseconds? Whoa, it's twice as fast. So that's something. It's gone from 69 microseconds in pure Python to 67.5 microseconds by just putting %Cython at the top, to 30 microseconds by getting rid of some of the Python objects and doing things directly ourselves. So that's a significant speed up, factor of 2. It's not a factor of 100 or something, but it is still a potentially important speed up. Though for a lot of things you do, this sort of work is not necessary. A factor of 2 may not be a big deal at all, especially when it's your own code. When you're writing code that's going to go in the core library of a system like Sage, then a factor of 2 could matter a lot, because a lot of people will call it in their own work. If you're just writing your own code that you're going to play around with for a couple of days, it probably doesn't matter at all. So you have to decide when you're trying to make things fast how much work you want to put into it. So it's twice as fast. Now the big question is, what is taking all the time? Of all these steps, which step is taking all the time? So I'm going to figure out which step's taking the time fairly naively. I'm going to do something very stupid, or silly. Oh, by the way, there are memory leaks in the version I wrote up here, if you look. I allocate all kinds of GMP objects, and I never free them. So that's another thing to worry about. This, as I wrote it, would leak memory. So in other words, when you type mpz underscore init, it allocates a chunk of memory where that thing is supposed to sit in C. If you don't put a corresponding mpz underscore clear, then that memory will never be deallocated. So I don't know if we can see this with the timer, but there's a function get memory usage, which tells you how much memory you've used. Let's try timing this, see if that goes up at all. Right now it's 150, I'll do it down here. It's still, it's part of this is probably the granularity of the thing. Let's try just running it a lot of times. It's an extremely small memory leak because you're just leaking a few bytes each time, but they add up if you do it enough. Ooh, look at that. Just like that, by doing this loop 100,000 times, the memory that my system's using, even though I have nothing new, to show for it, has gone from 153 megabytes to 158 megabytes. The reason is because I started playing around with some C library calls that allocate, memory wherever they want, and I really did do. This isn't a setup. I actually did forget when I wrote that code, and I never put the corresponding deallocation calls in. So every time it calls that function, it allocates just a little tiny bit of memory for this power of 10, and also for this number mod power, this other number that's taken to the, in other words, for end of the D mod a power of 10. So a little tiny bit of memory is allocated for each of those. But if you do a little tiny bit of memory, and you just forget to free it, and you do that 100,000 times or 1,000,000 times, you end up wasting a lot of memory. So that's an extremely noticeable amount. And that just took a second or two. If I do this again, so we can see how many seconds it would take to completely devastate your laptop. So look, 9 megabytes in 6 seconds. And if your laptop has only a gig of RAM, multiply that by 100, and you let a calculation that's doing some sort of loop like this run for a couple of minutes, and suddenly you've run out of memory. And you have nothing to show for it, because it's just wasted memory. So I'm trying to give you, a sense of some of the drawbacks of programming against a C library. On the other hand, it can be twice as fast. So there are pros and cons. So it's twice as fast, and we're in big trouble because of memory leaks. So the main Sage release manager is this guy, Michael Abschoff. He's a German guy, and he is really obsessed with tracking down and removing memory leaks from Sage. So when anyone submits code to Sage that has memory leaks, he gets really annoyed. Okay, so this is the same function. The only difference is I put in code to give back the memory that got allocated. And timing it, it's actually faster. Look at that. 25.5 microseconds versus 30 microseconds. It's exactly the same code. The only difference is I'm not leaking memory. That should seem a little counterintuitive to you. How can it be that forgetting to deallocate the memory makes your code slower? Any ideas or thoughts? Yeah, E.
Maybe there's some sort of caching?
Yeah. Basically. I can't tell you exactly what's going on, but allocating memory is pretty expensive, but allocating and freeing memory, it's hard. To be very naive, it's easier to find memory if you just freed some than to find brand new memory, which is what you have to do over and over again. Using up a lot of memory is slow. Yeah?
Can you have a string function in the other one?
Sorry, what? Oh, that's a good point. Looks like I forgot the string. Maybe that's the difference. Let's see. That's possible, actually. It could just be the string. In which case, never mind. But it still is the case often. Might not be as dramatic as this, but it is still the case that leaking memory can make your code slower.
It's 0.1.
Hey, 0.1 microseconds. Let's try this a few times. It might be. It could just be the resolution of the timer. It's looking like it's about the same. That said, it still is the case that, believe it or not, leaking memory can, in fact, make things slower. A dramatic case of this would be, suppose you start leaking memory and then you end up having disk thrashing or something. Then it'll be slower. But in this case, it's actually not at all. And you are paying a slight price for clearing these. Okay, so it's taking a little bit of time to do the clear. Okay, and also the point of having the string not in here was to illustrate that though this takes some time, this is not dominating the time. The difference between having this and not having this was about 5 microseconds. So you could probably reduce that a tiny bit by trying to rewrite this as some much more clever C library type code. But it's completely pointless because something else is taking most of the time. So let's figure out what is taking most of the time. So it could be just calling a Python function at all takes a lot of time with those inputs. So we'll make an empty function that does nothing at all. This will give us a nice lower bound on how fast we could possibly make this function. And see what happens. So the fastest we could possibly make the function if we were incredibly magically talented is 294 nanoseconds. There's no possible way that we can be faster than that. That tells us just something about the overhead of the function call. That's all it's telling us, that it's a few hundred nanoseconds. Really, really tiny. So that's not the problem. Let's try another version where we do, let me reformat this from my fonts. Integer creation. So remember up here I had some code right here that creates a sage integer and then puts the power in, it sets that sage integer equal to the power. The reason I had that code is because I wanted to be able to call stream on it. I didn't want to have to mess with calling into the GMP-C library to turn a GMP number into a string and then turn that string into a Python string. So I just wanted to save a little time by doing this. Not time in the sense of runtime, but development time. Because I suspected that the powering would be the problem. So let's see what happens if we just get rid of this. Don't make a Python integer at all. Just put a GMP value here, and then skip doing the string conversion. Let's see if this speeds everything up dramatically. Because if it does, then that means we need to do a little more work and completely get rid of any Python calling right here. Okay? So let's see what happens. So this is exactly like the other function with the change that instead of making a sage integer, which is a Python object that wraps a GMP integer, we just make a GMP integer. And then raise n to the power of e, mod a power of 10, get s. And notice I'm not actually returning the string. I would have to do a bunch of extra work to return the string, several more lines of sort of C code. So let's see if this dramatically speeds things up for this benchmark. And it doesn't. I mean, remember the overhead of the string conversion was about 5 microseconds anyways, so this gives us almost no speed up at all. Now finally, let's see what happens if we remove the powering statement, since we wonder if that's really taking all the time. Okay, so I'm just going to take the code, comment out that one line, run it, and see whether it's dramatically faster. If it is, then I can make a conclusion, namely that most of the time is being spent here, and the only way I'm going to make this code significantly faster is by making that one function significantly faster. And I'm not going to do that because it's part of the GMP library, and everything in there is extremely fast. Whoa, it suddenly went from 25 microseconds down to 829 nanoseconds. So that's where all the time is being spent on this. There's a little overhead with the other things, but this is it. I mean, it's right here. This is the place where the time's being spent. And that's a good thing, because if you have a function and almost all the time is being spent in one single call to a C library that's been optimized for many years, and is kind of the canonical industry standard C library for doing something, then you're in good shape. So that basically concludes our story. So here's the final, somewhere we should have the final function. Well, I guess 7 actually was the final function. We just wanted to prove to ourselves that this was the right thing to do. So this was the best thing to do. You could possibly shave off a tiny bit by changing this, but without getting rid of that one line or somehow rewriting it to be something better, you're just not going to be much faster than what we have already. Okay? So that's where all the time's being spent. So we've done our job. This function is twice as fast as the pure Python one, and we're good to go. And now let's just compare the beginning to the end. So how did we do? So remember, this was our original benchmark. And I can't try 10 to the 50 with our original function because that would take forever, since it literally in memory would have to write down 3 to the power of 10 to the 50, which is a number that has like a lot of digits, so, if you think about it. So you can't do that. But at least we could try the original benchmark. So there it is, working on the original benchmark. This one, it takes a while. So 184 microseconds per loop versus, 184 milliseconds per loop versus 8.77 microseconds per loop. So dividing these two numbers, there's a little difference from when I did it last time. We'll see that even on that sort of simple benchmark we started with, we've gotten a lot faster. So it's over 20,000 times faster. And that's a combination of changing our algorithms several times and converting some of the code from pure Python to Cython. But by far, the biggest improvement in speed was by changing the algorithm. That gave us a factor of 10,000. Then we got an extra factor of 2 by doing a whole bunch of work, introducing bugs for a little while, memory leaks, etc. And that extra work is worth it in some cases, and in other cases it isn't. You just have to decide on a case-by-case basis. But even more important, you have to try it a few times so that you know what to expect, or at least have a friend that's really good at doing it. All right, now let me show you something else. This profiling section in the Python library reference is something that I strongly recommend that you look at. And you can either read the whole thing through and learn all about all kinds of profiling things, or you can read the Instant User's Manual, which is a one-page document all about doing profiling of Python code. Here's the entire thing right there. That's it. And it's specifically designed for people who don't want to read the manual, which is probably almost everybody here. And certainly can understand that. So you might think, okay, so if you know much about using programming tools, you'll realize that a lot of the things we did, like putting in explicit timing statements and commenting stuff out, a lot of that can be automated. So you don't have to profile your code that way. That's just the most naive possible way of profiling code. It is good to become fluent at using that sort of method because it'll work in essentially any context at all in any language, which is valuable. It's a completely generic method. You have to do a lot of reasoning about what you're doing. So you have to think, okay, by commenting this out, I can tell whether or not this piece of code is taking a lot of time. So it's kind of fun because you do a lot of deductive reasoning, which of course everybody here likes doing. But there are much more sophisticated tools like the Python profiler, which I'll show you in just a second, which is described here and here. So these are various profilers, and what they do basically is every single time that the Python interpreter does something, there's a hook that will call some other function. So what they do is they hook themselves into that, and then they record every single Python function call, and then give you a report about how much time various things took. And it's pretty easy to use. Let's take our first, geez, that's not a very good function. It's missing the body. Let's take the very first, there it is. Let's take the very first version of our function and then profile it. And that's what you see. So what you get is it runs the code, which you should put in quotes. Otherwise you'll profile evaluating the output of the code, which is not very exciting. So it tells you how many times each function is called in the course of running the code, etc. And in this case, you see that the string part is being called the most. We could try instead profiling the second function where we greatly improve the string thing. See, there's more functions that get called, but now something else is being called more. actually unclear to me what exactly, etc. So you can do this. And then the final example. This is a little snippet of code I just wrote, which you give it an expression, and it will profile it. So here's what happens when you type 2 plus 2. Here's what happens when you type divisors of this number. Oops, that's a syntax error. Divisors of that number. And what it does is it gives you, in some sort of sorted order, every function that gets called in order to evaluate that expression, and the amount of time it took. I'll do one more. Say factor 2 to the power of 137 minus 1. So, that one didn't take very long. 197 minus 1. Oh, it didn't take very long. How about compute the 10,000th Bernoulli number? Okay, so here you could see that most of the time was spent in some function called burnfrac, which is a C library call. You could do factorial of 10 to the 6th. And what it does is it runs it, and then it tells you where most of the time is spent. This is another boring one, because most of the time is spent in one particular C library call. Here's one that might mean nothing to you, but I'll compute some thing from number theory. And here there's a lot of different functions that get called. So you can look through it and try to figure out where the time is being spent. So this is a more sophisticated way to do profiling, but you really want to use a combination of the two methods when you want to speed up your code. Okay, all right, so I'll see you on Monday next week. And also I have office hours upstairs for 1 hour. You too.
Later on. Yeah, I thought you were actually in